We're now on section 4 of the session, which is a short one, but for me a very interesting one at least. We have Jeff Pettis from the US Department of Agriculture, I nearly said the EPA, who's going to be looking at multiple stressors, taking bees as a case study. Jeff is an entomologist, and he's been looking at bee colony health with respect to multiple stressors for some time. Interestingly, as well as serving on several committees, which seems to be a norm in this business, he speaks a lot to the media about pollinator declines. Jeff.
Yep. Thank you. I'd like to thank EFSA for the invitation to speak today, and I'd like to thank the audience for your stamina. So maybe you heard the rumor that during the discussion there will be free beer to facilitate the discussion. So it's good to stick around. I would like to open with, I'm an entomologist, a biologist, and as some of the speakers have pointed out, we like to measure everything. But in working with Environmental Protection Agency and other regulatory agencies, it's important that we as scientists provide reliable information to those decision makers. So what I'm going to talk about is pollinators in general, and talk about some of the complexities of understanding pollinator biology and how they may be exposed to toxins in the environment and these multiple stressors. So my talk outline, I'll talk very briefly about pollinator decline. I'll spend some time on bee biology, honeybees, bumblebees, and solitary bees, some of the diversity of their biology, some of the challenges that we have to risk assessment, to the risk assessment process. Then I'm going to spend a little time on two studies. One is my own with colleagues at University of Maryland, where we followed bees into pollination contracts and looked at real world exposure in pollination contracts in the US. And the last study is a recently published study in canola in Sweden, which I thought was a very well replicated field study. And I'll conclude with a few remarks. I was in the US back in the early 2000s, and colony collapse disorder, bees were dying at a fairly high rate, honeybees. And this caught the media's attention. But this honeybee phenomenon is only one part of worldwide pollinator decline. There's a lot of debate about what's driving pollinator decline in general. I'd just like to point out that colony collapse disorder is unique to honeybees, and it's also almost unique to the US. It hasn't been widely reported in other parts of the world, but it did grab the media's attention. And honeybees as a test organism are very complex, both in their biology and the host of pests and pathogens that they have. As was just pointed out by the previous speaker, honeybees have been used as a test organism for pollinators, and the reason for that is they're available all over the world and we can rear them. But they suffer from a wide variety of pests and diseases. And it's also, I'll point out later, it's impossible to get clean stock. We never have honeybee colonies that are completely pure. It's just not possible. So a little bit of comparison between honeybees, bumblebees, and solitary bees. Honeybees live in these large colonies, single queen, 30,000 worker bees, and again, they overwinter, so they're a large annual perennial colony. Bumblebees, by contrast, have very small colonies, up to 300 individuals, and they break apart in the fall. Only the queen overwinters. And in a solitary bee, as the name implies, there's no colony, single female does most of the work, and the reason I'm pointing these differences out is some of the protection goals for pollinators are to protect pollinator diversity. So you have to ask the question, are honeybees the best test organism? And I'll try to weave that throughout, that perhaps they're not the best test organism in all cases. With honeybee colonies, they store honey and they can store pollen for winter, so they can have the storage capability. That's why humans have used them for thousands of years, mostly honey and wax. Bumblebees, by contrast, used almost all the resources that they gain throughout the year, and only the mated queens overwinter. So the mated queens are the survival stage in most bumblebee colonies. And in solitary bees, either the queens or the pupae are the overwintering stage. And the last bit in this comparison is how they utilize food resources. Honeybees can store pollen in the comb. You see the yellow part in the comb. They also store honey. That's very important if you're doing long-term studies with honeybees, because they can collect a large amount of material on a specific crop and utilize it 2 or 3 months later. So you can't always look at when the material was collected and see the effect. And we've learned that with longitudinal studies. They also have a very long flight range, 5 to 10 kilometers, so they're sampling a huge amount of the environment. Bumblebees, by contrast, they do store pollen and nectar, but they utilize it right away. And they have a much shorter flight range. And with solitary bees, it's even, sometimes shorter flight range, and they use pollen collected from plants. They create a pollen ball most often and lay an egg on that pollen ball, and then the larvae develops on that pollen that's collected. So they utilize the pollen and or nectar in quite different ways. So some of the challenges to the risk assessment process. The Environmental Protection Agency, one of their protection goals is the need to protect pollinator diversity. So again, I asked the question, are honeybees the best model? There's a very nice poster downstairs that looks at a wide variety of pollinators exposed to different toxins and shows that Bombus terrestrius, one of the bumblebee species, is highly sensitive and others are less sensitive. So, and honeybees fall somewhere in the mid-range. But we have to ask ourselves, if the pollination protection goal is for all pollinators, pollinator diversity, can we rely simply on honeybees? And then again, how do we test multiple lines of evidence that pollinators are being affected? So I've worked closely with EPA over the past 10 years or so, and they have at least 3 protection goals relative to pollinators. The pollination services that they provide, so that's mostly managed pollinators, but wild bees provide a lot of pollination services. Diversity, or pollinator diversity, is one, and honey production, actually honey production for the beekeeper. Those are all protection goals that help guide us in what we're trying to do with pollinator protection. As I pointed out earlier, honeybees in any situation are never clean, and the best we can do is try to control the pests and diseases that are in a certain stock of bees that we use for testing, whether it's laboratory or field testing, but there's always confounding factors. It's impossible to eliminate all the bacterial infections and mites and diseases and focus on one single aspect. So we don't have clean stock. And so how do we consider these other stressors that are affecting the honeybee colony, especially if we're going to look at survival of the colony as an endpoint? It's really, really difficult to do. The other thing that we've relied heavily on is to test individual bees, individual worker bees in an LD50 test or whatever, even a behavior test. And how does that individual behavioral change, or LD50, how does that relate to the colony? Is it fair to say, well, we see an effect on individual, is that really affecting colony survival? EFSA held a very nice colloquium back a few years ago, trying to move towards understanding the drivers of pollinator decline and how do we take into account these multiple stressors. And that's available at the EFSA website. I've already pointed this out, but I think it's very important because since honeybees have been used as the surrogate non-target pollinator, how do we relate this individual testing that we see to a colony level effect? Even in my own work, we've shown individual effects on disease transmission or increased pathogen levels in individual bees, but does that always translate into a colony level effect? And it doesn't always happen. The reason we use individual bees is they're easy to manage. We can emerge them in large numbers, know their age, we can control a lot of the variables. When we go to the colony level studies, they're very difficult to carry out, very difficult to control all the variables in the field. And again, this is just a slide just kind of summarizing some of the differences in the biology, this wide host of bees that are out there that we're trying to protect. I haven't mentioned the ground nesting bees showed there in the middle, but things in the soil then would expose ground nesting bees to additional stress, stingless bees there in the middle as well. So there's a wide variety of biologies that we must consider in a regulatory context. Now I'll switch and move into this study on crop pollination, where we moved honeybee colonies to different crops in bloom and simply collected the pollen that was there. And then we used a secondary stressor, a pathogen of honeybees called Nosema. It's a gut pathogen very similar to Giardia in humans. And we used that as a secondary stressor to see if the pollen they would consume on the crop were having effects on the pathogen. So we simply went out where honeybees were on these crops, collected pollen with a pollen trap at the front of the hive, and we collected on almonds, apples, blueberries, cranberries, cucumbers, and watermelons. We then identified the pollen that was coming into those into those hives. We analyzed the pollen for pesticide residue. And in the laboratory, so that was a field component, just looking at what they were collecting. In the lab component, we fed newly emerged bees with the pollen, and then we challenged them with this nosema gut parasite. So we have a single pathogen. The bees in this case are disease-free. They're newly emerged. They haven't been exposed to nosema. We have some nice negative and positive controls so we have negative controls for our nosema. But we simply expose the bees to the nosema parasite with clean pollen or the crop pollen, and then look at the growth rate of nosema in those bees. Before I get to that, this is the pollen ID from the different crops, starting with almond, where the proportion of the pollen from the crop is shown, and you'll see that with almond and apple, both old world species, the bees were collecting a great deal of almond and apple pollen, so from the crop of choice. The other thing you'll look at, the rest of them, blueberry, cranberry, watermelon, etc., they're almost collecting no pollen from the crop. And if I'm a grower, I'm looking at that and say, well, I'm not getting any pollination services. That's simply not true. There's just not the available pollen in those flowers that the bees can collect in surplus. What they're doing is moving pollen on their body, and they are doing pollination. But these first two, almond and apple, are old world. Honeybees are old world, and they collect a large amount of the pollen. But also remember, I'm feeding pollen to these bees from these other things, and there's almost none of the crop pollen is there, and yet we're going to see pesticide residues in that pollen where we're really not collecting it directly from the crop. So this is the number, simply the number of pesticides detected is in the white bars, and the grayer bars are the pesticide load in parts per billion, not taking into account the toxicity, just simply the total amount of pesticide. And again, so for apple, the very first one, the white bar, there were 15, on average, 15 pesticides of some kind in that apple pollen. And that was primarily apple pollen. But I'll contrast that with blueberry. Blueberry had 3 or 4, and there's almost no blueberry pollen in that sample. Cranberry as well had 12 on average, 12 pesticides detected, but almost no cranberry pollen in that. So now we'll take this pollen with these different mixtures. We're going to feed it to bees and challenge them with a pathogen, and we're going to see the effect. And the reason I'm showing you all this is we tend to do the regulatory process one compound at a time, which is the only way we can expect the companies to do it, one compound at a time. But the real world is that bees are being exposed to multiple stressors at any one time. This is a breakdown of the classes of compounds that we were seeing, and there are 2 things of interest here. They have an asterisk because they were both significantly different. The fungicides as a group, all the bars represent apple going across the different crops. Fungicides were highly represented in the pollen and significantly different from all the others. And the neonics, a group of keen interest in the media and stuff, was only present in the apple pollen that we collected. So only apple pollen showed any neonics. And I point this out because we'll see in the analysis in a bit, the fungicides seem to play a significant role. So this is just a breakdown by class of the things that were present in the pollen. Again, we're going to take newly emerged bees, and we're going to feed them the nosema. We're going to wait 12 days and just look at the nosema levels after exposure. Now, with this kind of mixture of pesticides, how are we going to assign that this pesticide had an effect and this one didn't have an effect? We're going to use kind of an epidemiological approach and look at relative risk. So we're just going to ask, if this particular compound was present in the pollen, what's the relative risk that the nosema levels went up or down? And this is just an example from human health. Lung cancer linked to smoking, relative risk is really high, whereas coronary disease is down to 3 to 4. So for me, it's a new way of looking at things, but for you in the audience, it's the way you do most of your studies, is just relative risk analysis. And again, our challenge is nosema, and we use the same dose, applied it to all the bees, and we just look at the relative risk of this nosema disease increasing. And so for a few of the compounds, the 3 on the top are all fungicides. Chlorothalonil and pyraclostrobin both had over 2 relative risk that the nosema would increase. This is a compound used by beekeepers, and it also increased nosema, and this is an ag chemical. Imidacloprid had virtually no effect on nosema infection. So this, along with studies that we've done earlier, is pointing us to that fungicides used commonly in blooming crops can be a problem, in this case interacting with a pathogen in bees. So there can be these interactions, and again, it comes back to the thing when you're trying to understand bee biology or bee deaths or bee losses, we can never exclude, we can never get clean stock, and we have to take into account these interactions that could occur. Now I'll spend just a few minutes on this, I call it the Swedish study, led by Rundloff et al., and it's published this year in Nature. Sweden had never had seed-treated canola, and they were looking to maybe use seed-treated canola in Sweden, and they did a 2-year study. The beauty of this study was it was well replicated in the plot size, and they used 3 different bees to look at effects. They used honeybee colonies, bumblebee colonies, and solitary bees in this study. They had 16 total plots. They were paired across southern Sweden, so they were paired in space, and they replicated it 2 years. For honeybees, they had 6 colonies per plot, and they had multiple bumblebee colonies, but I don't, off the top of my head, remember the exact number. This is just a bit of data from the bumblebee growth pattern. And so this is days running along the x-axis, and the y is the weight gain of bumblebee colonies. So the black dots are colony weight gain across time in the control non-seed treated. And you see the seed treated, basically those bumblebee colonies stayed the same, they didn't grow. What they were able to show with this study was that both the bumblebee, the smaller colonies, and the solitary bee colonies were both affected, or the solitary bees were affected. The honeybees were not. So honeybees on the same plot were not affected, no significant difference, whereas the bumblebee and the solitary bees were. And I think that comes back to colony size. So again, honeybees, the way they measured it, no significant effects on the honeybee colonies. The bumblebees, they had impacts on growth and reproduction, and the same for solitary bees. And I think the key to that, and the key to this colony size difference, is just that honeybees have a large buffer. We estimate that 20 or 30% of the workers are extra, they're in reserve. So a honeybee colony can take a lot of insult or a lot of impact and not actually have an adverse effect. At least that's one of the explanations. So some of the challenges to risk assessment process, we're trying to protect all pollinators while using honeybees primarily as an assessment endpoint. And I think we need to consider that. I know EPA is looking at including a solitary bee and bumblebees as part of that process. And again, I would say that honeybees are not always the best model, and we need to continue to look at multiple lines of evidence for just understanding pollinator decline. This is a bit of data just from the EPA. They're looking at things like weight of evidence, and we've heard that throughout some of these earlier talks throughout this conference. Taking into consideration all the data and to try to reach a decision, so not just relying on specific things, but a weight of evidence approach. The other way is to use colony simulation models. So, and I know EPA is working also with EFSA closely on looking at simulation models to try to identify endpoints and also gaps in our knowledge so we can go out and test those. One last thing is, as a risk assessor, you're providing information for a risk manager to make a decision. This is again from EPA. The scientific risk assessment we have to keep in consideration is only one of several factors that is considered in having a product on the market or not. So, but we have to get that risk assessment right. We have to get that correct. So, summarizing, I just want you to keep in mind that all pollinators are threatened. They have a lot of different life histories to consider and in the testing process. The honeybee in particular is a very complex organism, and in general, our best survival metric is the survival through winter. And we often don't run studies that long to look at winter survival, but that would be ideal. I think we do need to test both multiple pollinators, but also the formulated product. We don't always test the formulated product. And we need to use realistic field sizes, But when you get to field, to tier 3 studies, those plot sizes can get very expensive right away. So we have to know what we're doing and use good replication and good field sizes. And lastly, I think that modeling can, in fact, identify gaps and help us to hone in on those questions that we really need to address in trying to protect pollinators. So with that, I'll thank you. If we have time, how are we doing on time? I have one little better end on a high note. I have 1 minute. Yep. I'm going to end on a high note just because I always talk about bees dying. In doing some of this work, we were looking in honeybee colonies, and we noticed a kind of an interesting phenomenon in the stored pollen. And we called it entombed pollen, and we gave it a name, and we published on it in 2009. It's kind of hard to, this dark area here are pollen cells that the bees have taken propolis, sticky plant material, and they've covered it up. And the reason they've covered it up is because of high fungicide content. So this is the same comb, that's normal looking pollen, and on the same comb they've covered this pollen up. So I'm just going to show you the pesticide profile from this pollen and that pollen from the same comb from multiple hives over time. Just remember, we're calling this entombed. The bees have sealed it up to not use it. And the pesticide profile for pesticides, this is a control. There's almost nothing present in that yellow pollen. In the covered up pollen, there's fluvalinate, coumaphos, and chlorthalonil, a fungicide. So the bees are recognizing when the pollen was contaminated, and they're covering it up. So in a way, that's a great note. I mean, that they can recognize something and seal it off. So anyway, just wanted to throw that in. Thank you very much.
Thank you, Jeff, and especially for that end note. Okay, we have a couple of minutes for questions, so we can take one or two. I'll start over here.
Thanks very much. Wopke van der Werf, Wageningen University. In your table of relative risk factors, there were sub-compounds that increased relative risk beyond one, beyond one. Mm-hmm. Some compounds reduced it. How do you interpret that? Is that scatter or are they beneficial?
Actually, I've been asked that several times. So the ones that reduce it, we've actually known from some testing in the 70s that there were certain fungus. Nosema is closest to a fungi. It's been reclassified. And there was some work in the 70s looking at fungicides to control Nosema. So yeah, it can have a beneficial effect. Yeah. Yeah.
Okay, I'll take one more question.
I'm from Florida International University.
I missed you the last time.
I know a lot of bees are shipped to other places around the United States. How do the changes in environment affect the bees in your studies? Did you look into that or no?
There's been a few published studies on, you mean the transportation itself, the stress of transportation. There are some studies that have been published, very few on transportation stress. The one thing I'll say about that, especially about the US situation, we've asked beekeepers how many colonies they're losing for 10 years now. And we thought that the migratory beekeepers would lose more bees than the stationary beekeepers. These are large commercial beekeepers. 8 out of the 9 years, the migratory beekeepers lost the same amount of colonies as the stationary. So transportation itself, while it certainly impacts bees, it's not a driving factor. We're not driving our bees to death. We may be working them to death on the pollination, but we're not driving them to death. Yeah.
And a final question from here, please.
Nick Birch again, James Hutton Institute. Thanks for a very interesting presentation. My question is about the variability within one bee species, like honeybee. And there's a recent paper showing sensitivities to, say, neonicotinoids can be times 30 different between, say, Italian bees and bees from Israel or somewhere else. So this applies to both field studies and lab studies. How can you be sure that just doing one lab study or one field study with one population is really representative?
A very good point. There's even pheromonal differences between the queens, like we call them races, the races of bees. There's differences there. So we try to declare what bee we used, but ideally you might work across there are more northern races of bees, the Caucasians and then versus the Italians. It'd be nice to do it with multiple races of bees. It's not always possible, but there are differences in response, yes. All right, thank you.
Okay, thank you very much. We conclude this section of the session.